Good morning, everybody. My name is Augustin Fonts, and I am a product manager on the Android UI framework team. And if you're wondering, I do work on Android text and fonts. And yes, fonts is my real last name. So with that out of the way, let's begin. So today we want to cover a few things. First, we want to convey how we think about APK size and a couple of metrics that we think you really should care about for the success of your app. We'll also walk through a series of best practices that are going to help you reduce your APK size today, as well as show you a number of new tools and features that we are going to introduce this week that will also help you keep your APK size down. So let's get started. One of the things you'll see today is that we have a really diverse group of people from Google. People from the Android team, from the tools team, from the Play team, internal developers at Google. And the reason we have so many people on stage with different backgrounds is because we really think that APK size is super important. And it's something that we see as something you have to take care of from the design stage, the time you build your app, the time you publish your app, and the time that that app gets delivered to a device. So let me tell you a little bit about kind of the two dimensions that we think are important for APK size. First is the download size. So this is the size of the application when it's in the Play Store and it gets delivered to the device. This is highly compressed, and we'll tell you more about how we do that. And that allows us to save a lot of size on the wire and users' data. Now, as we said, download size is pretty small, but there's another concept that's important, which is installed size. So installed size is what happens when you actually download the app, unpack it, and then compile it and optimize it, which expands the application significantly, yielding a download size that is sometimes 2 to 3 times even bigger than the download size. And so it's something to really think about is what is the footprint of your application going to be once it's installed on the device. Now, let's talk a little bit about why you should care about both download size and install size. On the download size front, this is something really important because what happens is when a user goes and installs an app, they're going to see that loading bar and they're going to see the actual size of the application. And what we see is the larger the app, the more sort of user regret that happens. And a lot of people will go and actually back out of it and cancel. And so what we see is that up to 20% of downloads fail or get canceled rather when applications are over 100 megabytes. And so you really want to keep that download size small to ensure that you get as much distribution for your app as possible. The other one to think about is install size. Now, install size has a sort of a similar phenomenon, right? So users are going to be filling up their phones with photos, videos, more applications, and at some point they're going to try to install a new app, and they're going to realize that they don't have space for it. What's going to happen at that point is they're going to go hunting. They're going to go to their settings, they're going to look for their apps, or if their disk is full and they try to download an app from the Play Store, even the Play Store will suggest that they remove some applications and they give them a list of suggestions. What we see here is that, again, apps that are pretty large, especially 100 megabytes or above, are 8 times more likely to be removed from the device. So this is really going to hurt your re-engagement if your app is more likely to get uninstalled. So I hope that I've given you sort of like a little bit of motivation to think twice, maybe 3 times about your APK size, go back and think about what you can do. And what we want to show you today is a number of ways you can follow to reduce that APK size. Some are going to be existing practices that have been out there for a while, and we're going to hope to summarize and make them really compact for you. And others are new, and we're going to show you those. So let's roll up our sleeves. We're going to be working with the Topeka app. You may have seen it in our code labs or sample apps. Topeka is a quiz app, so it has a lot of resources, a lot of assets. It also has a good chunk of DEX code. This is what gets compiled and expanded on device. So it's definitely a good opportunity to tackle DEX code and make it smaller due to its outsized impact. In a typical production app, you might also see some shared objects. This doesn't happen in Topeka, but we'll cover a little bit also what you can do with your shared objects. So at this point, I'd like to hand it over to Shai, who's going to run through a lot of these concepts and best practices in real time. So hopefully you see that it's not too difficult, and it's something you can do with your app.
Thanks, Mr. Fonts. So here we have our app built and running. I can press Build APK to get an APK, and then press Analyze APK to crack it open and see what it's made of. I already have it open here. So an APK is just a glorified zip file. Here we can see all of its contents. We can browse through the resources folder to see all of the large drawables that really dominate the most bytes in our app. We can look at classes.dex, that stands for Dalvik executable, and see all the code for our app, as well as of some of our dependencies. We can even look inside resources.arc and see, for instance, all the translatable strings and styles and dimensions and other resources that end up in resources.arc. We can even look at the Android manifest binary XML and decode that. Notice that there are two columns with size information. First, we have raw file size. This is how much every particular item contributes to the size of the APK as a file on disk. The second is download size, which better represents how much bytes the user will actually have to download from Play in order to install your app for the first time. Now, you'll see, for instance, that for resources, these numbers aren't very far apart, because resources are dominated by large PNGs we have for drawables. These don't benefit from further compression, whereas for some other items, entropy is typically lower, and so the gains from compression are higher. We're going to show you a bunch of tricks you can use for this particular app, which we're going to use right now on stage, and we're going to show you their impact on the app size. For your own app, your mileage may vary. Rather than memorizing these particular steps, if there's one lesson that you should take home from this talk, it's that optimizing your own app size begins with sort of finding out what's in it and tailoring to that. All right? So, first step we're going to take is to use ProGuard. ProGuard is enabled by default for release builds, and it's a whole program Java optimizer. What it does is basically three things. So one thing it does is it optimizes your code in ways that don't change the functionality, but do change the representation to make it more compact. For instance, it might inline certain methods to their call sites if it's deemed to be more efficient. In some cases, it is. Another thing it does is it obfuscates names of types and methods and fields where the original name doesn't matter, so that long names are replaced with short strings like A and B for efficiency. I know we all like to give our Java classes long names in our packages, but this shouldn't get in the way of efficiency. And then lastly, there's dead code elimination. Now, this is the most important role of ProGuard, so pay attention. Think of your program as a graph of classes, methods, and fields as nodes, right? And calls or references as edges. So Android apps have well-known entry points at activities, services, broadcast receivers, content providers, and optionally a custom application class. If these classes are in your app manifest, then the platform can call into them. So ProGuard marks them as live because this code can execute at runtime, right? ProGuard then propagates liveness across the program via references. So it's basically a tree exploration sort of algorithm, and anything that is reachable from those seeds is considered live. Then whatever code remains, the complement to that, is presumed dead and will be deleted from your app unless you specify otherwise. This is important to be aware of. So let's look at the impact of that. Here's what happens when we run ProGuard on Topeka. You'll see that most of the code is now completely gone. So for instance, if I look at the support library here, I see that it's considerably smaller than it was before. We can also get these results using the APK analyzer. We can compare one APK with another. Here we have numbers in raw APK size, and over in the chart on the slides, I have it as download size. Thought you'd appreciate that. So if we look closely inside the DEX file, you'll see what I just showed you, that most of the support library code is gone, and most of the rest is obfuscated, right? So what is going on? Why is this happening? There we go. Why is this happening? ProGuard allows you to choose what libraries you want to use without having to worry so much about all the stuff in the libraries that you don't need and how it might bloat your app size. In this case, we're using the support library v4 and v7 and notifications and design and all kinds of assets. And we're only using a subset of the support library. So everything we're not using just gets torn away at build time and eliminated. Now, some of you might be thinking, This is nice, it's a nice benefit, but the optimizations make debugging more difficult. So hold that thought until the next demo. What we've done for code, we can do for resources as well. Same principle here. Resource shrinking extends the concept of ProGuard's dead code elimination to resources. So in this example, drawables whose references are reachable from live code are kept in your APK, and then everything else is deleted. Now our app is almost 4x smaller. And this is no mistake. All we've done is tweak 2 lines of Gradle, but what we get is, once again, things that go into sort of the transitive closure of dependencies of our app, but are not actually useful to the app. So once again, this is due to features included in our dependencies that we don't need. The support libraries, in this case, contain a lot of design assets that you could use, but Topeka isn't, so we can just make all the dead weight go away. But we can do even better. So if you recall, we saw that in the resource folder, when we were looking with the APK analyzer, we have drawables for different screen densities. What's going on? The Android ecosystem is diverse, with support for different displays and different CPU types and other such things. By default, when you build an APK with all the material to service as many devices as possible, we call that the universal APK, you get a larger APK than what's actually needed on each particular device. Every specific device that runs your app will only use files for its particular density, and if you have native code, then for its particular CPU architecture and other such things that APKs can vary on. Fortunately, you can split your build across these dimensions, right? And then upload multiple APKs to play, each one tailored to a particular device type. Here we intentionally look at the APK built for XXHDPI density screens, which contains the largest PNGs, because this is the largest APK that we're building for this app in this example. You'll see that the difference is significant, even when comparing the universal APK to the largest split that we have. And of course, the difference is more pronounced for HDPI, MDPI, etc. Speaking of PNGs and densities, we can do even better with Vector Drawables. Tell them, Gus.
Thanks, Shai. So now we just saw that there's a way to deliver a smaller app by chunking it up and delivering multiple of those apps. Now, that's a great benefit to APK size, but it does come at a cost for your build process as well as your QA process, and that might be something that you're not quite ready to get into. There's an additional approach you can follow to reduce the amount of size you carry with your assets, and that's to use Vector Drawables. Vector Drawables would basically is serving a vector into your application, so there's a single asset that can serve up all of the densities. For this particular asset on screen, the vector drawable is actually smaller than the smallest density PNG, so it's quite nice. And this is, I would consider it to be kind of a medium complexity vector with somewhat complex paths, but not necessarily gradients and things like that. The thing that makes, I think, Vector Drawable very usable and exciting today is that in support library 23.2, we introduced support for Vector Drawables backwards compatible all the way to API 14. Also, with N, we introduced gradient support of Vector Drawables, so hopefully that gives you kind of a wider range of things you can do with vectors. Now, one thing to keep in mind with vectors is that they can increase your RAM and CPU load, especially when you first start up the application. So if you have an app that is, a series of assets that are pretty complex, then you probably want to do kind of a bit of a performance test and make sure that you're not sacrificing a lot of performance in exchange for a smaller app size. Now let's look at the savings. After substituting most of the PNGs with vector assets, which this app is very good at because it's all flat images with relatively low complexity, we see that Vector Drawables is a little bit better than multi-APK. That kind of makes sense, right? Because we're carrying just a single asset in the application. Our advice would be that you consider what kind of image assets are in your application. So if they are relatively simple and flat, you should definitely consider it. And then that also simplifies your build and QA process so that you only have to produce one APK to upload to play. So let me hand it back to Shai for one more best practice.
Awesome, thanks. So finally, we're going to see a specialized trick for resources.arc. That's Topeka's ARC file. So Topeka's ARC file, as we saw, is small, but we'll make it 2x smaller with one line because we can. So here you can look inside the ARC file and view all the strings translation, and also hear live on stage. Now, you'll notice that some strings only appear in English. For instance, there's going to be sign in here and sign out. But other strings have as many as 82 translations for them. Why is this happening? So the support library folks went out of their way to localize their strings. And kudos to them, because this is the right thing for a library to do. A lot of apps go to similar lengths to translate their own strings, and you want the libraries to kind of line up so that the app isn't half translated, right? Not the case with Topeka. It didn't bother with anything but English, which is typical of our sample apps. Translating your app is a good way to reach out to more users, and we absolutely encourage that. Google translates all of its apps to as many languages as this. But a half-translated app can make a poor user experience. And then what's worse is these empty spaces actually use up bytes in our ARC file by indicating sort of null entries across 82 locales for all the strings that weren't translated. So what are we going to do? We're going to get rid of them. And we can fix all of this by simply stating that we only want to retain English strings. And then all the half translations just disappear right out. So I know this is hard to see the difference, but if you look under your seats, you will find a pair of binoculars each. Made you look. As promised, ARC is now 2x smaller, although in the big pictures, this doesn't do much since it was small to begin with. On the other hand, I've seen real apps that are 40% ARC. True story. So once again, your mileage may vary. Now let's take a look back and appreciate the fact that our Topeka app is now 5x smaller than when we started, over 5x, in fact, and it's not even 10 a.m. Thank you, thank you, thank you. What I've shown you so far is all existing functionality. Now I'll hand it over to Clara to tell us about some new stuff.
Thank you, Shay.
New stuff, Clara?
Hi, I'm Clara Vallari. I'm a tech lead on the Android UI Toolkit team, and I work on fonts. So here I'm very excited to introduce, today we're presenting downloadable fonts. Fonts are a source of bloat for apps, and we know that. They're heavy files. They're stuck into your app, and you need them because you need it for your UX. That's fine. We figured out that actually most fonts that you are bundling in your apps are not even optimized for mobile. So about half of the APK of the file size that you're adding is not even something we're going to use in Android. So that's a shame. Also, we looked at the Play Store, and we figured out that the top 25 apps that bundle fonts are actually bundling about an average of 500 kilobytes in fonts that we own in the Google Fonts catalog. We're like, OK, we should be able to do something with that, right? Never mind the fact that several apps are bundling the same fonts, and you're duplicating them in your device. So that's where downloadable fonts comes in. You've typically bundled fonts in your app, and that causes your APK size to increase. With downloadable fonts, we're introducing the concept of a fonts provider. There you go. Can we go back, please? There you go. Fonts provider is a separate app that is not yours, that is, its own mission is to fetch fonts for you, cache them, and serve them to you when you need them. This means that you can stop bundling fonts in your app and trust the font provider to do it for you. The way this works is all apps can just contact the font provider via the fonts contract APIs. These are available in Android O and in Support Library 26 Beta 1. By doing this, all of the apps are contacting the same font provider, which means we have one copy of the font that all apps are using at the same time. What does this mean, really? Well, it means we save memory, because we're only loading the font once and sharing that memory between all apps. We're also saving APK size for all of these apps, because they don't have to bundle the font. And we just have one copy. We're obviously saving disk space for the user, because all of your apps are smaller. And we're also saving network if you are actually fetching fonts from the network, as only the font provider is the one responsible for fetching these. This is available in support library today, and I'm very proud to announce our very first font provider, which is available. It's a great collaboration done with the Google Fonts team, where we're providing the entire Google Fonts catalog, and that is 800 fonts available to your app to use, free from APK size. Isn't that amazing? That is done through Google Play Services. It has a tiny caveat. This is in Google Play Services v11, which is currently in beta. Next, I want to hand it over to Wojtek to give you a very smooth demo of how Android Studio have integrated with downloadable fonts.
Thank you, Clara. So, hi, everyone. My name is Wojtek. I'm a developer advocate working closely with the Android Studio team. And today, I want to walk you through some of the new features we have in Android Studio and tools that are relevant to APK size, and hopefully will let you keep your APK size down. So as Clara explained, downloadable fonts are a great way to make your apps look pretty without adding the bloat to your APK. So let me show you how easy we can add downloadable fonts to your apps in Android Studio. So here I have opened one of the layout files from the Topeka app. And you can see if I click on the text view, here on the right in the layout inspector, I can actually go and change the fonts. So I scroll down, and if I select more fonts, there's this new picker in Android Studio 3.0 that we just announced yesterday. And you can see here, you have access to literally hundreds of fonts from the Google Fonts catalog. And if I just choose one, here I can select the downloadable font. I can see the font immediately change in the preview. But then, what's more, Android Studio also includes support for binary and XML fonts project structure, and see a preview or edit it. So that's one thing. But when we're on the topic of resources, we are also making changes to AAPT, which is the Android Asset Packaging tool. This is the part of the build system that processes and packages all your resources into the APK. And with Android Studio 3.0, we are introducing a new version of AAPT, AAPT2, which has a few neat tricks for reducing your APK size. So first up, we have something we call version collapsing. So normally when you develop an app, you add resources for various versions of Android. Typically, you want to have different colors or different styles for the different versions of the platform. And that also happens, for example, in the support library, which you normally bring into your apps. But as you develop your app and time passes, you normally start raising your min SDK version and kind of restricting the versions of Android that your apps run on. But these resources still remain, especially if they come from external dependencies. So they take up unnecessary space in your APK. So with AAPT2, we are introducing version collapsing, where AAPT2 can actually figure out the min SDK of your app and get rid of all these resources that are unneeded. And what's more, it can collapse the configurations in your app to reduce the size of the resources file even further, only including the resources that your app actually will need. Next up, we have resource deduplication. So another example. Here, I'm showing different translations for your app. And it happens sometimes that for some languages, for some configurations, like here French and French Canadian, mostly the translations will be the same. Most of the words are exactly the same, except for just a few. And it doesn't make sense to actually keep these duplicate resources in the resources file. So what AAPT2 will do now is we'll find those duplicate resources, get rid of them, and let the system default to the default configuration. So this is version collapsing and resource deduplication. AAPT2 does a couple of more internal things. Like it starts using UTF-8 for text, for string resources included in XML files like layouts and the binary resources file. It has a smarter cruncher. This is the part that reduces the size of your images by optimizing them. And if it finds that your images are actually already pre-optimized and the output of AAPT2 crunching would be bigger, then it just discards those bigger versions and uses smaller ones. So we aim to enable AAPT2 as the default in Android Studio 3.0 stable. However, you can try it now with the Canary U1 release. All you have to do is add this one line to your Gradle properties file. So I encourage you to try it and reduce the size of your APKs without doing anything. So like I said, you don't have to change a single line of code when you use AAPT2. But sometimes that's not enough. Sometimes you actually want to go in and inspect and change things in your app And you need tools to help you make decisions of where to actually go and make those optimizations. So like Shai mentioned before, one of the biggest changes you can make to your app to reduce APK size is enable ProGuard to shrink away code and resources. But when talking to developers at conferences like this, I often hear that it's very difficult to debug build problems and runtime problems that can stem from enabling ProGuard in your apps. And developers were really lacking tools that will let them inspect those problems in detail. That's why we're making some improvements to the APK analyzer in Android Studio. Let me show you on an example. Can we switch to the demo, please? So here I have Android Studio 3.0 Canary running on my machine. And one of the first things, I'm going to walk you through a few things that we're adding to let you better debug ProGuard problems. But we've also added some UI tweaks to the APK analyzer that hopefully will make it working with it even easier. So the first thing you might notice is we now have multi-dex support. So I can select multiple dex files and actually see a combined tree view of all the code in my app. So this is a very simple example. This is not the Topeka app. This is just an APK I created for the purpose of this demo. And you can see I can drill down into the source code of my app here and actually see all the classes that I have. And the app really has two parts. It's very simple. It just has an activity, and it has a fragment. The thing is, the fragment, the way I use it is I only use it from a layout XML file. And that will be important later. We've also made some other tweaks to the DEX viewer. So for example, we have some filtering options, and I can, for example, disable showing classes that are referenced from my file but are not actually defined in it. But moving on to ProGuard. So this is a debug build. This has, for this, ProGuard is not enabled. So I built my release APK. I run it. And the first big problem with the app is it crashes. It crashes on startup. I don't know why. It throws a class not found exception. And the second problem is, if I actually go and try to debug the problem, I can see, again, like Shai mentioned, that all the names of my types, of my fields, methods, they were all changed to strings like A, B, C. It's very difficult to debug the problem here. So what I can do now with the new Android Studio is I can actually load the ProGuard mappings that were created when my APK was built. So let me open the ProGuard mapping folder here. And now you can see the DEX viewer changed. First, I can actually see all the names of classes, packages, everything's back like it was in my original source code. Second, I can actually go here and see now that my blank fragment is missing. That's because ProGuard was not able to automatically detect that it's being used in my code. What's more, I can press this button here, which will let me show all the removed nodes that were removed by ProGuard. Yep. So I found the blank fragment here. It was removed. I right-click on it, and I can actually generate a ProGuard rule that I can that I can simply copy and paste to my ProGuard configuration. So I'm going to choose the first rule. It's the simplest one. I just want to keep the class and all its members. So I copy it here. I rebuild my app. And I open the APK after rebuilding it. I've loaded the ProGuard mappings so that we can keep things brief. I open it, and what's more, I can see that the blank fragment is not only here, it's shown in bold, which means it was explicitly kept by the ProGuard configuration. So that's the ProGuard support in Android Studio and APK Analyzer. But there's more. For real power users, you can actually now go and figure out how the classes that you use and the dependencies that you have pull even more code inside your app. So for example, I know that in my source code, I'm using this class called optional. But I've never used this one or this one. So why is it here? I can now right-click on any class or method and actually find usages and get a nice tree of dependencies and see that actually this present class is used by this method from the optional, which I'm using from my own create. What's more, I can actually verify that by opening my onCreate method and looking at the exact bytecode of that method. Now, I know not every one of you will need to use this, but if you work with very complicated build systems, if you do your own bytecode transformations, now you can actually analyze the bytecode that gets packaged in your APK. OK, can we switch back to slides, please? So this is available in Android Studio now. However, there are some more things that we're working on, and hopefully you'll get to play with them in the future. But now let me give you a sneak peek. So in the DEX viewer, previously we had only 2 columns showing the number of defined methods and reference methods, which is useful if you're debugging problems with multi-DEX. Not really problems with multi-DEX, but problems with the number of methods. We are adding a 3rd column that will show you the actual byte size per package, class, and even method. So you can see how the functionality you add to your code or the libraries that you pull into your code base impact the DEX size and APK size of your app. And the last thing is, Shai showed you how you can compare 2 APKs. But so far, the functionality was quite limited and only worked on the raw APK size. We're expanding the compare APK action to actually give you the actual update size as delivered by the Play Store from one version of your app to the other. And we even include the new file-by-file support that's been added to Play. And if you're not familiar with file-by-file patches, let me invite on stage James from the Play team who can explain it better.
Thanks. Hi, everyone. My name is James. I'm a product manager on the Google Play Store. Play delivers a lot of apps. In the last year, we delivered 82 billion app installs and even more patches to keep those apps up to date. We saw earlier in the presentation how app size directly correlates with install success, so users couldn't be giving us a more clear signal that they care about the size of these downloads. So in the last year, Play invested a lot in taking significant steps to reduce APK size for downloads and updates. I'm delighted to say that we had some great success, and I'd like to tell you about 2 of those in particular. The first was Brotli compression. Now, at Google, we're always super proud of our interns, but this one's going to take some beating. Our intern, Anna, took Brotli, which is a new compression format from the Google Research Europe team, and applied it to the Play Store. That one change reduced our data usage by 1.5 petabytes a day, compared to our previous method of using gzip for everything. This is crazy, right? We're super pleased with these results, and you can be sure we made Anna an offer to join us full time. Secondly, when Google Play updates an app, as the guy said previously, we deliver patches. So we started out by just delivering the full APK for each update. And then we switched to using diffing algorithms to generate deltas between old APKs and new APKs. Now, there's an issue with this. As we know, APKs are zip archives that are compressed. So take a look at this blob of text. On the next slide, I changed one character. Did you see it? It's in the top left, second word. Can we go back a slide? And then we see it again. OK, got it? Now let's look at the gzip -6 compressed version of that. Here's the first blob of text. And here's the second blob of text. And remember, we only changed one character. So let's see that again. It's pretty crazy. So a compressed version produces a massively different blob of compressed text. That means the patch between the two is very inefficient. So we decided to get smarter about how we generate patches. We launched a new system called file-by-file patching. We decided to uncompress the APKs and generate the deltas on the uncompressed versions. Every single file, file by file. This creates a far more efficient patch. And then we reverse the process when we apply the patch on the device. The result, we saved 6 petabytes of user data per day. On average, patches are now 65% smaller than the original app size, and some are even smaller. Netflix's original app is 16 megabytes, but the patch size was only 1 megabyte, a 92% saving. So with these 2 changes, we've dropped our data usage by 7.5 petabytes per day. To put that in context, that's roughly equivalent to 100 years of HD TV video every single day. If that doesn't give you an idea of the scale of Android in play, really cool. So next, we're going to take a different route. We're introducing Google Play app signing. If you join this program, Google Play will manage your key on your behalf and sign your app before delivering it to users. Now, once Google Play signs your app, we can go one step further, and we can provide app size optimizations. Now, you heard earlier about multi-APK and the stuff that's not required on each device. If I have a 32-bit architecture and a HDPI screen, then I only need the contents of the boxes in blue, and the rest of the APK is completely unnecessary for my device. With app optimizations, we deliver just the right content for each device. So if multi-APK is too difficult, too complicated, or you're doing it just now and you don't want to anymore, sign up for app optimizations and you know it, never need to again. You give us a universal APK, and we will automatically create an optimized APK for different devices on screen density and native architecture. Now, we're just getting started exploring this area. It's really early. But we've tried this out with a few apps that were in our early access program for app signing. And we expect the average savings to be about 15%. However, some apps see even better results. Deliveroo was 33% smaller after the optimizations, and the 7-minute workout app was nearly a half smaller. So we're really excited about this. We think this is going to be a huge benefit to users and developers. So how can you get these benefits? Well, app signing is available today. You can go out and get enrolled straight away. We are trialing app optimizations in beta with a few select partners at the moment, and we hope to widen the beta in the near future. So if you're interested in optimizations, please enroll in app signing. And if you'd like to find out more about these two, please come to our talk at 2:30 p.m. today at this, on stage 1 next door. So thank you very much for listening. Today we've covered a lot of the best practices that you can do to slim down your APK size. It's really important to users. So I really hope that you take something away from this and go and invest in making this better. If you'd like to find out more, you can talk to the Android and Play teams in Sandbox Dome C. Thanks again.